Hey everyone, solving Advent Code 2025, day 8. We're already coming towards the end of the Advent of Code, so yeah, let's see. Cool, so this is the output that they give us. I just pasted it there. Connect the junction box. Which junction boxes to connect such that the electricity can reach. So they have a list of all the junction box positions in 3D space. I see, so these positions are the XYZ coordinates. Straight line distance would be Euclidean distance. I think they give the link for this. The junction boxes that are closest. So by connecting these two junction boxes together, because the electricity is flowing between them, they become part of the same circuit. I see. After connecting, I see. So it is sort of a union find kind of problem, I guess, where where we would have. Okay, I'm not too sure where the circuits come from. Okay, because then they become part of the same circuit. So after connecting them, a single circuit which contains two junction boxes, and then the remaining of them remain in their own. I see. Okay. Cool. So by making the 10 shortest connections, there are 11 circuits, one with 5, 4. So multiplying them together. Okay. Cool. Alright, so let's just parse the data first. So the junction boxes, I'm not sure if the font is big. I changed the font just a slight bit, but this should be still sufficient to read it. Cool. So I do have a spatial library here. Maybe let me just have a z, which is also an int, and let's just have xyz coordinate as the tuple of x, y, and z, because I did not anticipate we would need it today. But this one should be a list of the xyz coordinates, right? So for this particular given line, the x, y, and z is equal to, let me just parse this as a function. We split by the comma for every v in this split. And then function boxes in x, y, z, and then we can return the function boxes. Okay. Cool. Well, this doesn't really necessarily have to be a union find, because logically we can just, for every coordinate, we kind of just search through the rest of the coordinates and we just keep track of which kind of parent they belong to. So in some sense it's sort of union find. So maybe I think it's a bit easier if I do just solve it as a union find problem instead. So we can have the parents, which is the list of the range of the length of the data. So let's just call this n. And then you have the ranks, which is the equivalent of 0 multiplied by n, right? Cool. So yeah, and then so basically what we want to do is for a in the range of n, I guess for I in the range of n of m. So they do tell us that there is 10 shorter circuits. So maybe we can say pick is 10 if it is test mode. Otherwise, let's do the regular input of 1000. So it's I plus 1 down to m. Okay, so what we want to do is, let's just declare find, and what find would do is if u equals to the parents of u, otherwise we can say that the parents of u is equals to the find of the parents of u, union, you have u and v, root u, root v is the find of u, find of v, root u is less than the ranks of root v, we want to merge it onto v, root v increments by 1, but the parents of root u is equals to the root v parent. Otherwise, we say that the ranks of the root u parents of root v is root u. Cool. So what do you want to do? Well, essentially, we want to find the shortest connection between all and basically get them to be grouped together. Basically for every junction box we find, let's search through everything else. If the everything else contains the closest junction box, what we want to do then is to union the two together so they belong under the same circuit. And then and we will just keep repeating this. Let's see. So you can just keep repeating this until you eventually find the most ideal scenario. So I guess what we want to do, well, pick is greater than 0, so this is where the pick can decrement by 1. I guess we should do something like for in the range of the picks, because I don't want to manage the pointer myself. Right? Basically, if union of I and j, if they're already in the same group, we can continue. The closest j, right? And then the if the Euclidean distance, so let's just have a function for that. Euclidean distance is the xyz coordinate b, which is the xyz coordinate. Let's just have this an int. Essentially the distance is every coordinate subtract to each other. So basically what we want to do is we want to just perform the, you can kind of see here that if we are calculating on a higher dimension, for example 3 dimensions, we would literally just take each individual point, right? So this would eventually be square rooted out, but what we want is to say a0, let's see, a at 0 minus b at 0, and then we square this answer, plus a of 1 minus b of 1, squared this as well, and then a of 2 minus b of 2, and we can square this as well. Cool. So if the Euclidean distance, I guess we can say closest is currently 10 to the power of 10, so assuming they're really far apart. So suppose that the Euclidean distance of the data of I, data of j is less than the closest. The closest is the Euclidean distance of data of I to data of j, and the closest j is equals to this j. Yeah, maybe let me just make this a private function. Oops. Oh, I can't type today. Cool and cool. Okay. So we say that the closest j is this, and at the end of it, if the closest j is not equals to -1, then we want to perform a union where I and j gets unioned together. Oh, sorry. Closest j. Cool. And this will keep performing the operation until we are done. And then what we are interested in now is to look at the number of the sizes of each of these. So what we could do is we could then go and check the size of each of the union sets and then verify to make sure that they are of a certain size. So let's just say parent sizes is this. There might be an algorithm for this, but I can't really remember it off the top of my head, so I think I'll just brute force this for now. But basically for I in the range of the length of n, the root of I is find of I, parent sizes, so I think this will be a good time to import collections, import default dictionary, because I don't want to manage it myself. Default dictionary of an integer. So the parent sizes of the root of I can increment by 1. Sizes, right? And then again, let me just run this. See if it worked. It did not work. Between a complex number and a float. Okay. Oh, cool. So what is up with this? Why did it tell me there is a complex number? Okay, let me just print out this output, because maybe I'm just like completely mistaken for what it's supposed to be. Okay. Huh. Ooh dear. Okay, so for some reason we managed to calculate a complex number. What was the two coordinates that we were looking at? Data of I, data of j. Huh. That's strange. 592 squared plus 817 minus 479 squared plus 812 minus 940 squared. What's wrong with this? Why would this? Okay, that's a bit weird. Why did it perform this operation wrongly? Ah, okay, I know why. It's because of this. Yeah. Okay. Cool. Cool. So we are calculating the distances correctly, so that's a good thing. Okay, let me just verify to make sure. Okay, so we have encountered them before. So what is the closest j? 16. Okay, maybe let me just verify that we are merging in correctly. Right. Okay, so we take 0. So the 0th coordinate. And we calculate. Ah, I see. It's because we're actually not looking for the closest global distance. We're actually looking for something slightly different. So So what we should do is to instead actually track this. So what we want to do is we want to try for all of the parents, for all of the pairs that are available. We said that the closest I is I as well. And the closest I is not equals to -1. So this would be the closest I and the closest I. Cool. Yeah, so you can kind of see here now it's slightly different, where we say we pick 167. Okay, then it's easier this way. So yeah, so we picked 167, 425, 690. We picked again 162, and then 431. And then the next one was 906 and 805, 9862. Yeah, because they were in the same, we kind of skipped over them, so we don't care. And then, yeah, so you can kind of see the final answer. There is 0 has 5 of them. 2 also has 5 of them. What is 2? 2 is 0, 1, 2. 2 is 906. Ooh, that's a bit off. 5, 5, and 2 and 2. Okay. 25, 50, 100. So that's really off. What's up with this? Let me see. Okay. Oh, wait, hold on. I think this is wrong, right? I'm not entirely sure, actually. I'm gonna cheat a little. I just take a look at the implementation of it. Okay, no. So we could do... So I'm trying to do path compression. And the... Path compression. It's this one. Okay, yeah. Okay, no. So I implemented it correctly. It is correct. I thought I messed up the implementation. Okay, cool. So it seems like it's kind of working. So why did it fail on this one? Okay, so what did they suggest? So the next two junction boxes are 425 but they're already in the same circuit, so nothing happens. Yeah, so I checked. If the find of I is in the same set as the find of j, we ignore it. Then we calculate again. If the Euclidean distance is closer, we pick this as the closer point. We set the 2. If the result... Okay, so the process continues, and then there are 11 circuit boxes between them. Okay, maybe it is easier if we just generate all of the pairs first. All pairs append data of I, data of j, and the Euclidean distance of data of I, data of j. And then we say all pairs sort lambda is x, cool. And then I am interested in printing out the all pairs. For P and the all pairs. Let's just do this. So that's neater. Cool. Yeah, so we can kind of see here that these are all the points we have chosen. So I guess just for a sanity check to make sure we are doing it right. It said that the very first one was 162, 817, 8112, 425, 698. Okay. Then the other one was connected was 162. Okay. Then the next one was 906, 560. Okay. The next one was 431, 425, but because these two got merged in, we skipped it over. This process continues for a while until they have extension cables. Yeah, so nothing happens means I skipped over it. Given that I already have my Euclidean distances and I've already sorted it, maybe it's actually just better or easier if I literally just union over this. So for all in the range of picks, what we could do is we could keep track of I equals to 0, length of the all pairs. No, if this shouldn't happen, so let me just raise an exception, say invalid state. Otherwise, we say that the all pairs of I can increment by 1. I guess we'll say while I is less than the length of the all pairs. Let's say that the all pairs is this. The ij and the I don't really care about the distance, I guess, so we can say this. If the find of I happens to be, no, let's say this is the P Q. If the find of P is the find of Q, we shall, if it is not the same, then what we want to do is we want to say union of P and Q. And then we increment. Okay. So yeah, so I guess we don't really need this, we just need I and J. Cool. The expression has type of this. This is strange. Yeah, we break out of this loop. Okay, cool. Basically, it's the same as the previous algorithm. I'm just interested in picking out based on a certain given order, right? The expression has type int. I'm not sure why this is the case, but let me just say pair of 0, pair of 1, yes. Not sure why the type was complaining about it. Cool. So yeah, so essentially we pick based on the order. So we pick pair and we can say working on, and let's just give it the pair, and let's just say else is skipping. Yeah, so we kind of see here, we say we take 0 and 19, so 0 and 19, which is correct. So those two got merged together. We worked on oh, why did it skip immediately? Okay, that's strange. Let's see. Okay, let's just do this. And you can say skipping on data of pair of 0, pair of 1. Okay. Okay, because we did not increment by 1 as well. Yeah, because we did a break. Yeah, so we say, okay, so we worked on these two. So these two got merged. We skip over this. We merge this. Okay. Let me think of why my answer is still wrong. Okay, so how many times did I operate on this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we operated 10 times on it. Okay. I might need to record down the pairs. I don't have my pen and paper with me, unfortunately. But let's see. We can just note that down here, I guess. So okay. Cool. So we now know. What do we know? Well, we know 0, 19 are in the same set. And then 7 went into the same set as well. 2 and 13 are now in the same set. 7 and 19 can skip. 17 and 18 go into the same set. 9 and 12 can go into the same set. 11 and 16 can go into the same set. 2 and 8 can go into the same set, so this one becomes this. 14 and 19 can go into the same set. Oops. 2 and 18 can go into the same set, so this would be 17. 3 and 19 can go into the same set. Okay. That is strange. 2 circuits. Okay. So logically the unions does actually work. It's just that the parents for some reason are not correct. Let's just print I and the root of I, and let's just see what this yields to me, right? Ooh, what's wrong with this? Okay, no. It's because of these. Okay, cool. So again, 0, 0. Oh, I need the output back. So 0, 0. 1 belongs in its own group. 2 belongs in its own group. 3 belongs to 0, so that's correct as well. 4 belongs to its own group. 5 belongs to its own group. 6 belongs to its own group. 7 belongs to 0, so that's correct as well. 8 belongs to 2, that's correct as well. 9 belongs to 9, that's correct as well. 10 belongs to 10. 12 belongs to 9. 13 belongs to 2, so that's also correct. 14 belongs to 0, that's also correct. 15 belongs to 15, that's correct. 16 belongs to 11, that's correct. 17 belongs to 2, that's also correct. 18 belongs to 2. That should not have happened. Okay. Okay. Is there a reason why we picked to merge 17 and 18, right? So 862, 61, 35, 984, 92, 344. Let's see, where were all my outputs? 17 and 18. So it has to be somewhere above, pretty much at the top. Yeah, you can kind of see here 17 and 18 was picked because it's 333. Was there any other stipulations that I missed? on this, because it does seem like 5 is correct. Yeah. Right, because you would have done 18. Huh. Okay. That is strange. Junction box to connect to. 20 junction boxes. As close together as possible based on the straight line distance. I see. Is there anything wrong with my Euclidean algorithm? No, I suspect we don't actually need to square it. Sorry, to square it. I don't think that changes anything though, so I'll just keep it as well. Huh. Okay. This is kind of weird to me for some reason, because it does not mention this being the main problem they have with it. Okay, wait. So this was 1 merge, 2 merge, 3 merges, 4. So 1, 2, 3. Okay, this is very odd. I'm not entirely sure why this is creating a problem. Because based on the Euclidean distance, everyone is as close as you can get already. Those are all the shortest possible pairs of points. Yeah. Oh, unless what happens here is that the distance now shortens because you got merged with a different circuit. No, they're claiming is that they want to focus on connecting pairs of the junction boxes, so not necessarily the yeah, okay, this is strange. I'm not entirely sure what's going on. Yeah, because let's see. Because if we were to look at the okay, let me just create a second pane so that I can nvim dump. Okay, so yeah, so the first thing we did was put 0 and 19 together. 0 and 7 got put together. 2 and 13 got put together. 7 and 19 got skipped because they're in the same set already. We put 17 and 18 together. We put 9 and 12 together. We put 11 and 16 together. We then put 2 and 8 together. So 2 and 8 is here. We then put 14 and 19 together. We then put 2 and 18 together. So this means this is the set now. And then we put 3 and 19 together. So this seems like it's actually correct. I'm just not entirely convinced why we chose not to pick that at all. Yeah, that's a bit strange for why we chose to do it this way. Let me just shrink the size a bit because I can't see my text anymore. Okay, let me just resize this as well. 20. Okay. That's because yeah, that's because we This is so strange. Why is it? Okay, let me just confirm that the 17 and 18 is the number that I was expecting. Right, so let's see. So let's have a calculator out. And we are saying I don't use the calculator here. Okay, cool. So we take 17 and 18, so it's 941 minus 862. I'll just use my phone for this. I think it's a bit easier if you just use your phone. Let's see. Yeah, so this would be 941. Well, no. I think the points are below here. Yeah, the points are here. So we take 862 minus 984. I need this to be scientific. So squared plus I'm just gonna highlight this row so that I don't forget where I am. Plus 61 minus 92 squared plus 35 minus 344 squared. Okay, so we take this number, we square it by a half, so it's 333. Okay, so this number is correct. This just does not make sense to me at all. There is a circuit containing 3 junction boxes. Circuit containing 2 junction boxes. It seems correct though. I'm not entirely sure what's up with the... What's up with this? This is so strange. This is such a strange problem. This does not affect anything. I do not know why I did it. Let's see. Did I calculate something wrongly? A of 0 minus B of 0 squared plus A of 1. Huh. It seems perfectly fine. What is going on with the algorithm? Okay, I don't think it has anything to do with my actual union find. Only for the fact that we are picking in this sorted order. I'm just wondering if there is something we should or shouldn't do with it, right? What if we don't care about this? No. We say this. Huh. Okay. Intuitively, this did not make sense. Because from the phrasing, they literally said the next two boxes. Yeah, so the next two junction boxes, because they are already in the same circuit, nothing happens. I will assume you didn't pick them, and you didn't need to connect them. But I guess you did. So that was the issue, I guess. So we can literally just do this, 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 and this is so silly. And based on this, we can say the answer is 1. For the we don't care about this. We just care about the value in the parent sizes values. We can return this and multiply by this. Cool. 80 is seemingly right. No. Huh. 4, 5, 2, and 2. The product of this would be 40, no? 4 times 5, 20. Oh, wait, no. Oh, the size of the 3 largest circuits. Oh my goodness. So we want to return the there's no product function. Return, let's just say sorted of this for the first 3, because I cannot be bothered to write this down. Reverse is true. Okay, cool. Yeah, I think fundamental idea was literally there. I think it was just a reading comprehension problem of trying to get that to work. But yeah, so let's see what the result gives me. 121, 770. Cool. They definitely do not have enough, so they want to keep merging. The first connection, of which is between the junction boxes. I see. Of the last 2 junction boxes that you need to merge. Okay, cool. So essentially, we can just copy over the whole behavior. We can simplify this later on, but for now, I just want to get this to work. But yeah, essentially, we don't care about picking n number of times. There is just a different, a slightly different, I guess, metric we use. So, let's see. All pairs. I equals to 0. I can increment by 1. Cool. So after we union, the way we know that 1 has everything basically is, I think, if we can check the rank. Pair of 0. find of the pair of 0. And the reason why I say this is because, yeah, it's because you eventually get to a point. Let's just return the, we don't care about this either. Yeah, so you can kind of see here that the rank keeps increasing to the number of, okay, this is a bit strange. No, because this kept merging onto itself. So I guess one way we should do it is we need to detect when both of the sets have merged into each other. And I'm guessing the way we achieve this is, so if you look at this example here and we keep merging, the rank of one of the roots eventually becomes the size of the input. So I guess what we could do is we could say if the ranks of the find of the pair of 0 is equals to the length of the data, or of 1 length of the data, we can break. I want to print out the pair of 0 and the pair of I, the all pairs. Oops. Okay, yeah. Let me just say data at this particular integer. 542. Oh, that's wrong. 29. So we claim that there is 29 mergers. This seems odd. 117. I see. Okay. Yeah, I guess the claim here is immediately after that merge. Well, I guess the answer is, I guess what we would do is we want to return the data at the all pairs of I minus 1 of 0. And this one we would take the x coordinate, I minus 1 of 1 of 0. Yeah, so it would be whatever this is. I'm a bit suspicious that this is right or wrong. It is not right. Okay, that's fair. But yeah, basically, we need to think of how do we know when both of them have become merged. I have begin to share the same set. Of the last two junction boxes. So I'm guessing in the I guess one way we could look at this is hmm. Okay, that is not what I wanted to check. To test. Yeah. So we originally had 2. Oh wait, no, but if you share the parent, it literally does not matter because the find would return the parent anyways. So I can kind of just do this. Yeah, so you can see here that that eventually it reaches 20, and then when we say, oh, we have found 20, which means the rank of one element is large enough for the rank of the other. Let me just do a check again that the rank is actually correct. Oh dear. Okay. Maybe I have just implemented union find wrong the entire time. But this actually makes a bit more sense. Although this does not make sense. Let's see. Okay, yeah, this does not make sense at all. So I'm just gonna stick to ones. I'm not sure why it did that. But okay, sure. Yeah, essentially we are merging into the roots which have it larger, but it does seem like that is not the intended behavior that we wanted. Sorry. Yeah. Well, no. It is theoretically supposed to be the ranks of the root U. Root E. Okay. This is a very silly answer, because clearly this should not be working. But let's see. Okay, let's just run through the let's just run through this algorithm, I guess. I want to print. I'm just interested in the order of which we merged these guys. Right? Okay, so cool. So we start with 0 and 19, 0 and 7, 2 and 13. Oh, sorry, so 7 goes here. 2 and 13, 7 and 19 is already merged. 17 and 18, 9 and 12, 11 and 16, 2 and 8, so 8 goes here. 14 and 19, then 2 and 18, but that also brings in 17. Let's see, 3 and 19, so 3 goes here. 4 and 6, we have 4 and 12, 4 and 5, so 12 and 5. But then because 12 is there, we can bring in 9 as well. 4 and 12. Where was I? 9 and 12, sorry. 9 and 12, 11 and 16, 2 and 8, 4 and 12, 4 and 5, 6 and 17. So because of this, now it is size of 4, 12, 5, and 9. Uh, 8 and 19 are together. And then we begin to merge this, so 0, 19, 7, 14, and 3. And then the very last step, I think, is 11 and 15, which then merges these two. Right, okay. So for some reason, oh, was that it? No, it's not. Cool. That is still not it. Eight, 19, 2, 3, 4, 5, 6, 7, 8. Oh dear, that's not it either. Okay. Okay, this is very strange. I'm not entirely sure what's going on. But I guess what we could do is maybe we could do something like tracking the unions, which at first is n, and if we don't need to perform, if they don't belong in the same group, the non-local of unions can decrement by 1. And then maybe what we do here is instead we check if the unions oh, it is. Okay. So that is what we needed, apparently. Cool. So this one here. Okay, cool. Yeah, so I guess very silly, but rather than performing all of the unions like this, one alternative we could have done is we could have literally just kept track of how many times we actually needed to union properly. And if we realize that that becomes a singular union, so it's one giant union, we stop the looping and we perform the operation. Cool. Because I have UFDS here, maybe let me just create a class for this. Init self n, which is an int. This would be none. Here you can have two functions, which is the find and the union. We can say that the self of parents, self of the ranks, unions is equals to n. Let's see, parents, self. Ranks is self ranks. Parents is self parents. And find is self find. Okay, cool. And then we can just check if the root of u is not equals to the root of v, unions minus equals to 1. Cool. So that just lets me control the UFDS very simply. We have UFDS is UFDS, we give it n. We can say UFDS union find Yep, and then yeah, and then just as some pre-processing here, we would say UFDS is this. We don't need this. UFDS union, if the UFDS unions happens to be below this. Okay, cool. Let me just verify to make sure both are correct. 1, 2, 1. Okay, cool. Yeah. I think like get pairs. We can say get ordered pairs, and we can say this is the data list of XYZ coordinates, where this would be a list of tuples of an int and the float. We can also generify how we perform this operation here. All pairs. This would be, you can say that n is the length of the data. I see. This should be a float as well. I completely forgot about that. Yeah, but we can just say all pairs is equivalent to the get ordered pairs of the data. And the same thing can be done for here as well. Cool. So yeah, I think today's problem was more fun. I think I've enjoyed today's problem a lot more than the previous few days. Essentially, this entire problem is a union find disjoint set problem where we want to keep track of which pairs of numbers are in the same group as each other. So that's a union find. That's a union. And essentially what we are doing here is we generate all the possible pairs. We pick the pairs that are of an appropriate, of like the correct size. And we apply the union, so we keep joining them together. So that's for the first part. Once you've joined all of them together, we can then calculate how many, what's the size of each of these unions by just going through and finding all of the parents, and based on the parents we can discover this. I guess like one way we could do is we could define a function for it, but I don't think we need to. And then once you've calculated all of the sizes of the parents, we can then literally just perform the multiplication this way. I guess like one of the ways we could do it is to literally say for pair in the all pairs up until the pick, and then I don't have to do that anymore. Yeah. So that was part 1. For part 2 is, it took me a while to figure out, but essentially what we want to do is we want to just keep track of how many unions there are, and if there's only one union remaining, it just means that we have already combined everything into the same set. So we keep performing the unions greedily until we eventually find that the unions become 1. Once it becomes 1, we have found the pair that causes the kind of giant merge together, and then we can just take the x-axis of these two. I think for the first part, the main thing that tripped me up was the kind of instruction where they said when they were in the two same sets, we don't do anything. So nothing happens, but I was assuming nothing happens means you don't actually need to connect, but I guess in this case we do actually want to connect it. It just so happens to remain in the same circuit. But cool. Today was more fun. Thank you guys so much for watching. I'll see you guys tomorrow.